We present Text2Motion, a language-based planning framework for solving geometrically complex sequential manipulation tasks. Consider the following problem. A robot is equipped with a library of learned skills and a large language model. It is given a brief description of the scene, followed by the instruction, "How do you fetch me any box from the table?" The robot's objective is to plan a sequence of skills that would satisfy the instruction if executed from the current state. Solving the task requires symbolic and geometric reasoning. Prior work in language planning for robotics proposes to solve such tasks with a language-based agent, which at every time step ranks skills by their usefulness and feasibility and executes the highest scoring skill. In this case, the robot first picks up the hook, but the grasp on the hook does not enable pulling the red box. The robot's only choice is to place the hook back on the table, returning the environment to its original state. This failure demonstrates that myopically selecting and executing skills cannot reliably solve long horizon tasks that contain geometric dependencies. A language-based planner must consider the feasibility of planned skill sequences before they are executed. In addition, a language-based planner needs a way to verify if a computed plan satisfies the natural language instruction, if it is executed from the initial state. The goal of this work is to construct a feasible manipulation plan and verify that it satisfies an instruction prior to executing any actions in the environment. In step 1, an LLM infers goal propositions that must hold in the scene for an instruction to be satisfied. In step 2, a hybrid planning algorithm, Text2Motion, is used to construct feasible manipulation plans by combining shooting-based and search-based planning techniques based on LLMs and geometric feasibility planning. A plan is only ever executed if the inferred goal propositions hold in the plan's final state as predicted by a learned dynamics model. We provide a walkthrough of Text2Motion's planning procedure. First, a human provides a language instruction to the robot. The scene is then converted to a textual description for the LLM. The LLM is queried to infer goal propositions from the instruction and the scene description. A proposed LLM-based shooting planner is optimistically invoked to generate k-candidate skill sequences. Geometric feasibility planning is performed to determine the feasibility of each candidate skill sequence. If none of the candidate skill sequences satisfy the goals predicted by the LLM, Text2Motion falls back to the very first iteration of greedy search, where the LLM is asked to generate k-candidate skills. The LLM scores the usefulness of each candidate skill. Geometric feasibility planning is then performed to determine the feasibility of each candidate skill in the context of the running plan so far. At the very first iteration, the running plan is empty, but it grows as skills are selected during search. The skill with the highest combined usefulness and geometric feasibility score is selected, and the future state resulting from executing the skill is predicted by a learned dynamics model. If the future state does not satisfy the inferred goal propositions, the shooting planner is re-invoked at this state to generate a new set of candidate skill sequences. If a goal-reaching skill sequence is found, the plan is returned for execution. Otherwise, the greedy search continues for several iterations until the future state predicted by the learned dynamics model satisfies the inferred goals, in which case we return a goal-reaching feasible plan for execution. We evaluate our method on 6 tasks, each with a subset of the following properties, being long horizon, having lifted goals, and having partial affordance perception. Long horizon tasks require executing 6 or more consecutive skills to solve. Lifted goals are goals where the instructions are not specified over concrete object instances, but rather over object properties and over the scene configuration. Partial affordance perception refers to the property where the skill affordances are difficult for the LLM to determine from the provided textual scene description and the instruction. We compared Text2Motion with the myopic baseline and the shooting-based planner. Text2Motion performs geometric feasibility planning with the provided skill library to ensure that earlier rack placements enable successful downstream placements. The reactive baseline produces actions with low value scores for the place on the rack skill, and in this case, places the object back on the table instead of on the rack. The shooting planner also completes the task successfully as it predicts a successful skill sequence from the instruction and scene description alone. For this task, we ask the robot to get two primary colored boxes onto the rack. For Text2Motion, geometric feasibility planning ensures that pick hook is executed in a way that enables the downstream pull box skill. The myopic baseline executes pick hook, but in a way that is not conducive to the downstream pull skill. In this case, it attempts the pull skill but still fails. The shooting planner fails to find a task altogether because the LLM did not deduce the use of the hook in any of its predicted skill sequences. In summary, our objective is to solve geometrically complex sequential manipulation tasks expressed in natural language. Prior work scores skills based on their usefulness and feasibility, however executes them myopically. Our core idea is to generate feasible plans and verify that they satisfy goal propositions inferred from natural language instructions. The result is Text2Motion, which can generalize to diverse long-horizon tasks with abstract goals and partial affordance perception. We hope this work spurs further research at the intersection of foundation models, robot skills, and long-horizon planning.